We look at a probability problem. Anna and Beat both choose a random number between 0 and 10, not including 0, but including 10. What is the probability that the product of their numbers is above 30, larger than 30? As a matter of fact, the problem is not stated very clearly yet, because we still need to know what kind of numbers they think of. We could go for whole numbers or for decimals. We really don't know about this. Let's solve these sub-problems individually. First of all, let's assume it's whole numbers. If it's whole numbers, then the problem is not that hard. We can actually visualize the situation. Anna and Beat both have 10 numbers to choose from 1 to 10. Thus, they get a combined total of 10 times 10, 100 cases. I marked the desired cases orange or golden in the diagram. You can clearly see it's an Excel table, and I had Excel color all cells golden that contain a number larger than 30. We can actually even count them, and we get 39%. 39 out of 100 cases are in our favor. Okay? Probability, Anna Beat choosing two random whole numbers. The probability that it is above 30 is 39%. Now, let's have a closer look if we allow decimals. First of all, let's look at decimals with exactly one digit after the decimal point. We can still plot the situation in Excel. It then looks like this. Well, it's a bit hard to see much. I also had Excel color the cells above 30 golden, so we can see, without actually seeing any numbers, we can see where the desired cases lie. Okay, it's not surprising that the shape is similar. It's a similar proportion of the whole of the situation from before with the whole numbers, but of course it's more finely grained. Okay, I can even have Excel count these cases. We'll see, or Excel tells us that it's 3,458 of such products that are above 30. It's easy, of course, to compute the number of possible cases. It's just 100 squared, 100 times 100, so 10,000. And again, we can compute the probability, desired outcomes divided by possible outcomes to find 0.3458 or 34.58%. Here you already see quite clearly that it's basically about the area, right? The area of the orange, of the golden part, divided by the area of the whole rectangle. Now we can make these sub-problems harder and harder by admitting more and more decimal places. If we had 2 decimal places, like 1.73 for example, we'd have 1,000 possible numbers to choose from, so 1 million possible outcomes, and Excel tells us that it's 339,499 times the case that the product is larger than 30. Okay, same with 3 decimal places. It's still possible to do this with Excel. Alright, noteworthy perhaps is if you look at the probability, they do not change significantly, and as a matter of fact they appear to approach some limiting number down here, right? It's 33 point something. If we had 4, 5, 6 decimal places, we would guess that the figure would still be in the ballpark of 33 point something. So let's go for this. What if we admitted arbitrary reals, like the root of 61 or pi plus ln 107, any real number above 0 and not more than 10. We can still illustrate this situation, despite the fact that we can no longer actually count possible and desired cases, or it's no longer discrete, it's continuous, right? But we can still visualize the situation. In a coordinate system with axes labeled A and B, we can plot all possible choices as points in this rectangle or in this square here, okay? Every point within this square corresponds to a particular choice of Anna and Beard. The area of the gray region is naturally 100, 10 times 10. Now, we can visualize the desired cases also. All points that satisfy A, B is larger than 30, well, they also satisfy that B is larger than 30 over A. Now, this gives us a chance to actually plot this. If we consider the function b equals 30 over a, we can plot its graph. It's the graph of a hyperbola, and then mark all points golden that are above this graph. We can surely compute the area that is marked golden. Well, it's a difference of a rectangle, the rectangle 7 by 10, okay, minus the area below the graph, which is the integral from 3 to 10 of 30 over a with respect to a. We're then left with the area we seek. The details are alongside on the left. What we get is 70 minus 30 times the ln of 10 over 3, approximately 33.88. And as we divide this by 100 by the area of the possible cases, we get 33.88%. And now please see how well this fits into our picture. 33.88 is the limit, so 3 decimal places has already been quite close to the limiting case. You might probably agree that it's actually easier to solve the problem for infinitely many decimal places for arbitrary reals than it would be to count the desired outcomes for, say, 6 decimal places.